Hello, and thank you for taking the time to watch our presentation. Today we will be discussing the use of electrolytic methods for groundwater remediation. Groundwater remediation is the act of removing a contaminant that has found its way into the subsurface water system. This process is needed when the contaminant poses a threat to human or environmental health. The stakeholders in a groundwater cleanup project are the people or entities who polluted the groundwater, the environmental agencies such as the EPA, an engineering firm to design a treatment plan, and the people who would be affected by the contaminated water, such as those who use drinking water from a well. You may be wondering about the possible sources of the groundwater contaminants. This figure may help you get an idea of the wide range of possibilities of pollution. Some say that the availability of work in this field is diminishing because of stricter regulations put on industries, but with such a wide array of possible sources, groundwater monitoring and remediation will always be necessary. Many of the items found in this image can also be found in Pennsylvania industries. Our group is trying to solve the problem of groundwater and soil contamination. Here you can see two situations that someone may encounter when cleaning up a site. On the left, the soil particles in the ground are completely saturated with contaminant. At this stage, it may seem easy to remove this contaminant, but after some time, water will fill some of the pores, and what is left is a thin sorbed film contaminant that cannot be simply washed down gradient. This example is the picture on the right. This contaminant will remain a problem until it is completely removed. The first step in remediating groundwater using electrolytic methods involves mobilizing the pollutant so it is able to be collected and then extracted. In our case, the pollutants are heavy metals such as cadmium, lead, and copper. In order to mobilize these metals, they must be desorbed from the soil particles and formed into ions. Ions are formed from elemental phase into anodes and using anodes and cathodes that are drilled and inserted into the ground in a matrix. A constant low voltage and low amperage is sent through the groundwater to cause many back and forth oxidation and redox reactions. The soil particles in this case actually facilitate these redox reactions by acting as a capacitor. Here's a photo of what the figure in the previous slide was showing. Note the number of charged cells and their spacing. The redox reactions will form an electric double layer on the soil particle, which will force the ions to enter the aqueous phase and be ready to be collected by the electric field. The target ions will be free to enter the bulk liquid and will be carried down gradient. The next step is electromigration. There is not a defined line between the desorption and electromigration steps. Rather, they are a continuous process. Electromigration is the movement of ions and ionic complexes due to an applied electric field. When freed, the positively charged ions will migrate towards the anode and the negatively charged particles will migrate towards the cathode. The force of the hydraulic gradient may work against the desired direction of flow, but in general, the electric attraction is such that it overcomes this gradient. Once the ions coat the anodes and cathodes, they can be removed from the soil to be cleaned and reused in order to reach the desired concentration in the ground.
When dealing with the influencing factors of electrolytic remediation, we must first consider the characteristics of the aquifer and the media that makes up this system. Particle size of the soil or rock must be understood before treating using this process. Grain size of soil particles and their aggregate structures affect the ability of soil to transport and retain water, air, or nutrients. Since electrochemical remediation is inversely proportional to the grain size, this means that any aquifer that is mostly silt, which is a particle considered to have a diameter between 0.002 millimeters and 0.06 millimeters, or clay containing, which is classified as a particle having a diameter that is less than 0.002 millimeters, will allow this treatment application to quickly pass through the media and is particularly effective in saturated, low permeability soils, which are often more difficult to treat with conventional chemical methods, such as chemical oxidation or soil flushing, because of their low permeability and their high sorption capacity. Likewise, any aquifer that is sand, which any particle that is a diameter between 0.06 and 2 millimeters, or gravel containing, which is usually a particle with a diameter that is larger than 2 millimeters but less than 75 millimeters, will slowly remediate and is not quite as effective with this process, since the size, shape, and inter-electrode distance will affect the removal rates of any contaminants. Any aquifer that contains a lower salinity is optimal for this type of remediation process. High salinity increases the power consumption per unit volume of water and is not the desired effect that is optimal for electrolytic remediation. Another advantage of using this type of remediation is that electricity will heat the soil, which will then result in decreased viscosity and a higher flow rate through the medium. Electrolysis can greatly affect the remediation site at hand. The change in pH of the soil as a result of this type of remediation can potentially negatively affect the system as a whole. When electromediation is used to remove heavy metals from the soil, metals may precipitate as hydroxides near the cathode where the pH is raised, which limits the remediation efficiency. To combat this, a length of tube filled with solution can be placed between the cathode and the soil, where the heavy metals can then precipitate into the water rather than into the soil. Another way to prevent the metals from precipitating into the soil could involve introducing a cation selective membrane to be placed in front of the cathode to stop the advancement of the hydroxyl front toward the anode. This process can considerably decrease the amount of water volume needed, while still ensuring the low pH conditions for the soil that is being treated. Although there may be adverse effects on microbial communities in the soil in this type of process, there can be a way to reduce this negative effect on the microbes and potentially harvest the energy from them as a result. Since we already have a solid electrode setup, it can be used as an electron acceptor or donor. A microbial electrochemical unit can be put into place and be used as a microbial fuel cell where energy can be extracted. The electrodes can be directly introduced into the aquifer and will stimulate the native microorganisms to accelerate the aquifer remediation process. Small MET systems can also be used to monitor the microbial activity in the aquifer. Any impedance of large metals in the remediation site can cause the effectiveness of the process to decrease and could negatively affect overall efficiency of electrolysis. Electrolytic remediation is sometimes difficult to target specific contaminants in the soil, so this process is commonly used for aquifers containing volatile organic compounds or VOCs, polycyclic aromatic hydrocarbons, certain metals, polychlorinated biphenyls, otherwise commonly known as PCBs, specific pesticides, and even some radionuclides.
In this next section, we will discuss how electrolytic remediation technology is implemented in the field. This technology is usually made up of four main components: the electrodes, the DC-AC converter, the electrolytic solution, and other miscellaneous pipes and wiring connecting the system. The system setup will consist of two opposite electrodes through which current flows. An anode is an electrode through which the conventional current enters. The anode will possess excess positive charge. Anions, or negative ions, are forced by the electrical potential to react chemically and give off electrons through the process of oxidation. These electrons then flow up and into the driving circuit. This contrasts with a cathode, which is an electrode through which the conventional current leaves an electrical device. The cathode is where the negative polarity is applied to drive the cell. At the cathode, cations, or positive ions, are forced by the electrical potential to react chemically and receive electrons through the process of reduction. In this case, the system will be set up in a bipolar fashion. The electrodes are typically installed in two parallel lines, one side with anodes and the other with cathodes, that are installed outside of the contaminated area to be treated. The electrodes can consist of either horizontal plates and pipes, or vertical pile sheets and pipes. Usually, raw materials are shipped to the site and then modified based on site geology and the size and shape of the contaminant plume. Common electrode array materials are steel sheets for cathodes and graphite sheets for anodes. For optimum treatment, electrode rows should be approximately 30 feet long and about 30 feet apart from one another. The depth of installation is dictated by the thickness of the contaminant zone. Typical DC-AC converters are 480 volts and 3-phase, which can power an average of 3 anode sheets and 3 cathode sheets. These converters produce a low voltage, low amperage electrical field that polarizes the soil or sediment, causing soil particles to charge and discharge electricity. This causes the redox reactions that occur at all interfaces within the soil, the groundwater, and contaminant and electrode system, mineralizing organics and increasing the mobilization of metals. Metals migrate to the electrodes where they are deposited and removed with the electrodes. The converter is controlled by an on-site computer system. When the direct current is applied between the electrodes, the charge on soil, water, and the contaminant will cause migration towards oppositely charged electrodes. In general, active electrodes in water cause an acid front at the anode and a base front at the cathode. The pH will drop at the anode and increase at the cathode. To prevent this pH imbalance, the electrodes are placed inside ceramic well casings, which are filled with an electrolytic or processing fluid. The electrolytic solution, which is also called a surfactant, not only keeps a balance of pH at the anode and cathode, but also can help move contaminants by acting as a conducting media or pore fluid. It can also serve as a means to extract contaminants and introduce chemicals or biological entities. Some processing fluids which have been used or considered in the past are acetic acid, humic acid, and gallic acid. By pumping, processing, and testing the efficacy of the electrolytic solution at each contaminant plume, it is possible to extend the life and efficiency of the system. Exhausted electrolytic fluid will be pumped out of the system. Auxiliary equipment for electrical and mechanical necessity may also be needed in order to run and install the system efficiently. This list may include, but is not limited to, a computer system, resistors, electrical meters, epoxy sealant, fluid collection tanks, copper cables, wires, and other installation machinery. The following video shows an example field setup for this type of electrolytic remediation.
Now we will be talking about the electrolytic methods that have been used in order to remove contaminants from the soil. Before undertaking electrolytic remediation at a site, several lab tests must take place prior to the process. Such tests include field conductivity, chemical analysis of water, chemical analysis of the soil, and bench scale tests. In our first case study, we have a former paint factory in Groningen, the Netherlands. The soil had been polluted with heavy metals such as lead and copper. The sludge was heavily polluted with paint particles. Lead concentration ranged from low estimates of 300 milligrams per kilograms of soil to high estimate of over 5,000 milligrams per kilograms of soil, while the copper concentration ranged from 500 to 1,000 milligrams per kilograms of soil. The electrode was set up in such a way that it had one horizontal cathode at 0.5 meters below ground and a row of vertical anodes at depth of 1 meter and spaced 1 meter apart. Current was applied in the area for 10 hours per day for 43 days, which reduced the lead concentration by 70% and copper concentration by 80%. However, the already acidic soil was furthermore acidified from electrolytic generation of hydrogen ions, resulting in the dissolution of more paint particles, which then acted as a new source of pollution. In the Netherlands, as our second case study, the soil was heavily polluted by zinc. Two cathodes were positioned horizontally in the soil, and three rows of anodes were placed vertically. For 8 weeks straight, current was applied, which led to a decrease in zinc concentration from 2,400 parts per million to 1,620 parts per million. However, the main objective was to reduce the concentration down to 200 parts per million. It was inefficient because in order for the electrolytic method to work, the metal ions had to be mobile. High buffering capacity of the soil made the zinc ions immobile, and as a result, the process was not as efficient. In our upcoming slide, a naval air weapon station in California had polluted soil placed between lagoons, which were separated by its surroundings by a high-density polyethylene wall. Three cathodes were centered between six anodes. The anode and cathode were 4.45 meters apart from each other. A constant current of 60 volts was applied for 20 days and then was decreased to 45 volts for 6 months. As a result, 78% of chromium of the soil volume had been clear. About 70% of cadmium in the soil was cleared between the electrodes. For our last case study, we have a site in Paducah, Kentucky, in the US, where they developed a new technique of removing heavy metals from the soil called the lasagna process. This technique created several horizontal permeable zones that provided treatment through contaminated soil matrix by adding different admixtures to the electrolytic solution. Such admixtures, like buffering solutions and oxidizing agents, are applied through a vertical system with an anode at the bottom and the cathode at the top. Horizontal electrodes led to the formation of lasagna layers due to the fracturing in over-consolidated clays. The first test proved to be successful, as it was able to remove 98% of TCE from the Paducah site.
So we'll be looking at some applications and limitations to electrolytic remediation. Electrolysis can be performed in situ as well as ex situ, meaning that you don't have to excavate the site if you don't want to, which can significantly decrease the cost associated with remediating the site. It has been successfully applied to media such as soil, sediment, sludge, and groundwater, and can treat saturated and unsaturated soils. Saturated soil is when a fluid, generally water, will fill the spaces between soil particles, and unsaturated is when a fluid, generally water, or air will fill the spaces between soil particles. Electrolysis can also target a specific area, and that is the area that is between the electrodes, and that allows control over which parts of the site is being remediated. Electrolysis can also be used to remove a wide range of contaminants, including organic and inorganic, and has been used to successfully treat VOCs, PAHs, SVOCs, PCBs, phenols, fuel hydrocarbons, and radionuclides. This electrolysis can treat man-made contaminants such as VOCs and SVOCs, which enter the environment due to automobile parts, disinfectants, solvents, cleaners, and it could also be used to treat naturally occurring contaminants, such as phenols, which are found in plants, or radionuclides, which are found in rocks. It can be also used to treat heavy metal contamination, and it is particularly successful in remediating mercury, arsenic, lead, cadmium, chrome, copper, nickel, and zinc. Some sources of these heavy metal contaminations include mining, corrosion, waste disposal, fossil fuel combustion, and agriculture. So, any sites that are contaminated uh, due to those sources could potentially look at electrolysis as a remediation technique. A major limitation to electrolytic remediation is soil particle size. Electrolysis is not very effective at remediating large particles, which can be considered to be sand and gravel, which are pictured in the bottom right. Large particles tend to remediate much slower than small particles. Small particles such as clay and silts remediate much more quickly and effectively, and a size of those particles can be found in the bottom left picture. Electrolysis can also affect the remediation site. It has been known to change the pH of the soil. The soil found near the anode can become more acidic due to a drop in the pH, and the soil near the cathode can become more basic due to an increase in the pH. This can adversely affect any microbial communities that are found near the anode or the cathode or within the electrical measuring field. Remediation using electrolysis may not be homogeneous. Some areas in the remediation site may be better remediated than others, and this is due to possible stagnant zones that can occur between the electrodes. Buried metals can also impede the remediation process. Metals can decrease the effectiveness if they are buried within the electrical measuring field, since they tend to interfere with the electroosmotic flux. And electrolysis does not target specific contaminants for remediation. If there are some, if there are multiple contaminants in the area, electrolysis tends to remediate the contaminants that are in high concentrations compared to the others. So, if there are any contaminants that are in extremely high concentrations, those may be remediated much more effectively and quickly than the others. And these contaminants may not be of interest. So that must be kept in mind when using electrolytic remediation.
And finally, I will be talking about the cost and availability of electrolytic remediation. To start off, here are some general factors that can affect the cost of removal. As mentioned earlier, there is an inverse relation between grain size and the time to purify the soil. The longer it takes will generally increase costs. The deeper the contaminant is in the ground, the more expensive it will be to drill down to and remove. The larger the volume of contamination is, and the more area it encompasses, will increase costs because more equipment will be needed to cover the entire area. The equipment required for remediation varies depending on the chemical structure of the contaminant. Since different remediation methods such as electroosmosis and microbial electrolysis require different equipment, each will have its own set of base costs. And finally, the longer the duration of the remediation will also increase costs based on equipment usage and power consumption. Depending on the type and the severity of the contamination, remediation costs can be anywhere from $50 to upwards of $400 per ton of soil that is affected. Both electroosmosis and microbial electrolytic cell remediation are available for field-scale implementation. The Tell Memorial Institute currently holds a patent for electroacoustic soil decontamination, which combines DC electrical and acoustic fields to remove contaminants, but that technology is currently only available at lab scale for now. All methods mentioned in this presentation only work for dissolved contaminants, so they are not effective for the removal of NAPLs. Thank you.